All right, let's talk about one of the most fundamental, most useful building blocks in all of electronics, the voltage divider. It sounds kind of technical, but trust me, it's a super simple concept, and once you get it, it opens up a whole new world of what you can build.
So here's how we're going to break it down. First, we'll look at the exact problem a voltage divider is meant to solve. Then we'll get into the super elegant two-resistor solution and the simple math that makes it tick. After that, we got to talk about a really important real-world catch called the loading effect. And finally, we'll go on a safari and see where these things are hiding in plain sight. Okay, so let's kick things off with a super common problem. You've got a power source, maybe a battery or a power supply, but it's putting out way more voltage than your little component can handle. It's a classic headache in electronics, and the voltage divider is one of the best tools to solve it.
So picture this, right? You've got a standard 9-volt battery. We've all used them, but the little microcontroller you're working with, it needs exactly 3 volts to run. Any more, and poof, you've got a tiny puff of magic smoke. You can't just hook it up directly. So what do? How do you reliably get that 9 volts down to a safe 3 volts?
Visit youtube.com/avidsystem and don't forget to subscribe.
Well, the answer is surprisingly simple. You don't need fancy, complicated chips for this. Nope. All you need are 2 humble resistors arranged in just the right way. Okay, let's actually walk through building one. You start with your input voltage. Let's call that VIN. Then you connect a resistor, R1, in a line that's in series. Right after that, you connect your second resistor, R2, also in series. Now the magic happens right in the middle, at that connection point between the two. That's where you tap into your new lower voltage, which we'll call Vout. Simple as that.
So what's actually happening here? Well, in any series circuit, the total voltage you put in has to get used up or dropped across the components in the line. In our 2 resistors, they basically agree to share that voltage drop. But, and this is the key, they don't share it equally. They divide it up based on how much resistance each one has.
Okay, that makes sense. They split the voltage. But how do we know exactly what voltage we're going to get? How do we control it? Well, that brings us to the math behind it all. And don't worry, it's really straightforward.
And here is the magic formula. It looks a little intimidating, but it's not, I promise.
Our output voltage, Vout, is just the input voltage, VIN, multiplied by a ratio. And that ratio is simply the value of the second resistor, R2, divided by the total resistance of both resistors added together. That little fraction right there, that's the whole secret. Okay, let's plug in some real numbers and see how this works. Let's say our input voltage is 12 volts. We pick a 1,000 ohm resistor for R1 and a 3,000 ohm for R2. We plug them into the formula, Vout equals 12 times 3,000 divided by the total, which is 4,000, so that's 12 times 3/4, or 0.75, which gives us exactly 9 volts. See, by picking the right resistors, we can dial in the exact voltage we need.
I mean, that seems almost too easy, right? A super simple, predictable way to get any voltage we want. But, in electronics, there's always a but wait, there's more moment. And for the voltage divider, that moment has a name, the loading effect.
So yeah, our math is perfect, as long as the circuit is just sitting there doing nothing. We built this thing for a reason, right? We want to power something with that 9 volts. So the big question is, what happens to our perfect little calculation the second we actually connect something to Vout?
And this is a classic case of theory versus reality. In an ideal world, with nothing connected, no load, our output voltage is rock solid. It's exactly what the formula says. But in the real world, the thing we connect, the load, isn't just a bystander. It starts to draw electrical current, and by doing that, it actually becomes a part of the circuit itself, and it messes with our math.
So here's what's going on under the hood. Whatever you connect, your load, has its own internal resistance. Let's call it RL. When you connect it to Vout, you're effectively adding that RL resistor in parallel with our second resistor, R2. And when you put resistors in parallel, their combined resistance goes down, which changes the whole ratio of our divider. Just look at the numbers here. It's pretty wild. In our original example, with no load, the bottom resistor was 3,000 ohms, and we got our perfect 9 volts. But now, let's say we connect a load that also happens to have a resistance of 3,000 ohms. The combined parallel resistance of R2 and the load plummets to just 1,500 ohms. And when you run the formula again with that new number, our output voltage crashes all the way down to 6 volts.
Whoa, that's a 3-volt drop. That is huge.
The 9-volt output we so carefully designed is suddenly only 6 volts, and that might be too low for our component to even turn on. So this loading effect isn't some tiny little detail you can ignore, it can totally break your circuit.
So how do we get around this? Well, there's a really good rule of thumb that engineers use. For this whole loading thing to not be a big deal, you need to make sure the resistance of your load, RL, is at least 10 times bigger than your R2 resistor. When it's that much higher, it draws so little current that its effect becomes tiny, almost negligible, and your V-out stays nice and stable.
Okay, now that we've got the theory down and the big gotcha, let's go on a hunt for these things in the real world. You are going to be so surprised at how often this simple circuit pops up.
You know that volume knob on an old amp? That's a potentiometer, which is just a fancy name for a variable voltage divider. Same for a lot of dimmer switches. They are also the absolute heart and soul of tons of sensor circuits, using things like light-dependent resistors to detect light or thermistors to measure temperature. And they're used constantly to give a steady, reliable reference voltage to sensitive computer chips.
And the way they're used in sensors is it's so clever. You just make one of the resistors, say R2, a sensor whose resistance changes with, for example, temperature. As the room gets warmer, R2's resistance changes, which changes the V-out from our formula. A microcontroller can just sit there and read that changing voltage, and from that it knows exactly what the temperature is. It's turning a physical property into an electrical signal.
You know, this quote really sums it all up perfectly. It's not just a neat trick. From the simplest job of just knocking down a voltage a bit to being the core of a complex sensor network, this little 2-resistor pattern is one of the essential tools in the toolbox. It's a true building block. So you see, this simple 2-resistor trick isn't just some abstract thing from a textbook. It's a practical, powerful tool for solving all sorts of problems and for turning the physical world into information a computer can understand. It is everywhere. And now that you know how to see it, the only question left is, what are you going to build with it?
Thanks for watching.